Hi, today's problem is common concurrence problems. In writing a program, we make lots of bugs. And so we're going to deal with the bugs in this lecture. There are two types of bugs. One is the one associated with non-deadlock, and the other one is deadlock. So first we're going to cover the bugs related to non-deadlock bugs. It make up a majority of concurrency bugs, and there are two major types of non-deadlock bugs. First one is atomicity violation, and second one is order violation. In atomicity violation bug, the desired serializability among the multiple memory accesses is violated. Let's look at the following example. There are two threads, thread 1 and thread 2. And thread 1 for check a certain proc info is not null, and if it's not null, then it prints out the proc information. That is perfectly okay. And there is another thread, and it performs, it assigns null value to the proc info field. Let's consider following order of execution. This one is first executed, and then the control is transferred to the second thread, thread 2, and thread 3. If this is the case, because thread 2 assigns null value to the proc info field, this one, the number 3 line statement, will issue the segfault, because it tries to access the pointer's address, whose address is null. So how can you fix it? We have to make sure that after you check the condition of the proc info, we have to make sure that this value does not change. So as a result, you can simply put the lock at the beginning of the execution and release the lock at the end of the execution. So you define a lock, and of course you initialize it, and before you check the condition that if the proc info is not null or not, you acquire the lock, and after you're done, you release the lock. Of course, at the same time, the thread 2, when you access and you assign the null value to the proc info field, you first have to acquire the lock and then release the lock. By wrapping up the code critical section with the lock, you can ensure the atomicity of the access to the shared variable. Another interesting issue is order violation bug. We have, in some cases, we have to ensure that two memory accesses are executed in the desired order, but order violation bugs is a situation where the desired bug between the two memory accesses is flipped. So A should always be executed before B, but if the order is not inferred during the execution, that might cause a problem. Let's consider two scenarios. There are two threads, thread 1 and thread 2. And thread 1 initializes the thread, and thread 2 it assigns a state of a thread to the local variable called the thread. So in these executions, we have to ensure that thread 1 creates the thread first, and then the second thread is executed. So the code in thread 2 seems to assume that the variable m thread has already been initialized and is not null. But in this part of the code, there's not any feature that enforces the order of execution between the two threads. So we're gonna use the condition variable to enforce the order between the two. So condition variable is used for just that purpose. So we first initialize the thread here, and then we signal that the thread has been created. This is a standard design pattern of using condition signal. So you use the lock we use the lock, acquire the lock, and update the state variable and send the signal, and then unlock the variable. So this is standard pattern. On the other hand, for thread 2, we lock the code, we acquire the lock, and check whether the condition is being held or not. If it's not held, then we have to wait. Once it gets out of the loop, it unlocks the code and assigns the state. So we have to make sure that this piece of code, let's say this is 2, and let me go back to the previous slide, and this piece of code, this is first one, should be used to ensure the order of execution between thread 1 and thread 2. Okay, so now we're going to talk about the deadlock. Let's consider the 2 threads. There are 2 threads, thread 1 and thread 2. And both of the thread acquires a lock, lock 1 and lock 2. But somehow the 2 programmers are writing their own code for thread 1 and thread 2 respectively. So somehow thread 1, the application code programmer locks the L1 first and then lock L2. For thread 2, another programmer locks L2 first and then lock L1. Okay, now the code is ready and the 2 threads are running in parallel. Consider the following scenario. Thread 1 is acquiring the lock 1. And then somehow the control is transferred to the thread 2, and thread 2 executes lock L2. And then next, thread 2 executes the next statement, lock L1, but L1 is not available here. So control is transferred to thread 1. And thread 1 locks L2. Okay? So we can draw the wait for graph. This is called wait for graph. Okay. Here, thread 1 holds lock 1. And lock 1 is wanted by thread 2. And at the same time, thread 2 is holding lock 2, and lock 2 is wanted by thread 1. So there are cyclic wait state. There are cycles in the wait graph for thread 1 and thread 2. There is cycles. Thread 1 is holding lock 1, and lock 1 is held wanted by thread 2. And in the meantime, thread 2 is holding lock 1, lock 2, and lock 2 is being requested by thread 1. So here, thread 2 is blocked at this point, asking and waiting for thread 1 to release lock 1. And thread 1 is waiting for L2, and that is being held by thread 2, and it waits for thread 2 to release L2. So this is what you call deadlock. So why do deadlocks occur? Of course, there is a cyclic dependencies among the resource usage, but why does it happen? In large code bases, it is possible that complex dependencies arise between components. And the second reason is due to the nature of encapsulation. Modern programming language is designed to hide details of implementations and make software easier to build in a modular way. But such modularity does not mesh well with locking. Why do deadlocks occur? Consider the following Java vector class in the method add/or. There are 2 vectors, vector 1 and vector 2. Thread 1, it calls vector1.add/or and v2 as a parameter. Thread 2, it calls vector2.add/or and vector1 as a parameter. In this interface add/or, it has to acquire the locks on both of the vectors, vector 1 and vector 2. But assume that it has some predefined order of acquiring the lock. For example, let's say here it acquires the v1 lock for v1 first, and then it locks v2. And then in the same manner for thread 2, it will acquire the locks on v2 and then v1. It will lead to the deadlock. So there are 4 conditions: the mutual exclusion, the hold and wait, no preemption, and circular wait. Mutual exclusion is a situation where threads claim exclusive control of the resources that they require. Hold and wait situation denotes the case where threads hold resources allocated to them while waiting for the additional resources. No preemption stands for the situation where the resources cannot be forcibly removed from the threads that are holding them. Circular wait, there is a circular chain of threads such that each thread holds one more resources that are being requested by the next thread in the chain. To prevent the deadlock to occur, if we can ensure that some of these conditions cannot be met, then the deadlock can be prevented fundamentally. But some of the conditions we cannot eliminate them. For example, the mutual exclusion. Some resources should be held in mutually exclusive manner, so we cannot eliminate this condition. And on similar manner, it is very difficult to eliminate the no preemption condition, because if a thread holds a certain resource, then it's very difficult for the other threads to preempt the resources held by another thread. So to prevent the deadlock to occur, the most widely used approaches is about eliminating the possibility of hold and wait to happen and circular wait to happen, so which I am going to explain in the next slide. First approach of prevention, deadlock prevention, is eliminating the possibility of circular wait. The way to eliminate circular wait is to provide a total ordering on lock acquisition. This approach requires careful design of the global locking strategy. For example, there are 2 locks in the system. Then all the programmer has to write the lock acquisition code based upon the numbers allocated for the lock. For example, lock L1 first and then lock L2. So we can ensure that if we can ensure that we acquire the locks with lock 1 first and lock 2 second, then we can prevent the deadlock. This is the Linux kernel code for file mapping. So at the beginning of the code, there is a sequence of writers that has been making contribution in updating the source code in 1994, in 1995, and in 1999. So there are a sequence of comments that says what's been modified and what's been added. At the beginning of the code, it specifies the order in which the lock should be held, right, like this. Here, and here, and here. So whenever you write the code, you are recommended to strictly following the order when you acquire the lock. So by enforcing the order in which locks are held, you can avoid circular wait situation. The second one is lock prevention. The second approach of preventing a lock is to avoid hold and wait. So deadlock occur when you require multiple resources, and when you already have some of the resources you want to acquire and you are waiting for the rest of the resources are to be allocated. One of the approaches to avoid hold and wait situation is acquire all locks at once atomically. So for example, you establish big lock of lock prevention and wrap the lock, the acquisition with a big lock, and then you can acquire the lock, all the locks at once atomically. This code guarantees that no untimely thread switch can occur in the midst of the lock acquisition. But there is a problem. This approach require all locks at once, requires to know when calling a routine exactly which locks must be held and to acquire them ahead of the time. So this is very difficult. And another problem of this approach is it decreases the concurrency. So another approach to prevent a deadlock is using the try-lock. So try-lock makes the hold and wait not to happen, and also at the same time it's very similar to non-preemption not to happen. So in try-lock, it first grabs the lock if it is available. Okay, and then it tries to acquire a second one, and if that is not available, then it unlocks the code immediately and then go to the lock. So this is the flow of the code. There is a label called top, and it locks L1, and then it tries to access the lock, acquire the lock using the function called try-lock. And if it's not successful, then it releases the lock that has been held by itself already. In this case, it unlocks L1 and then goes to top again. So it iterates this situation until it acquires lock 1 and lock 2. So a hold and wait condition does not happen in this scenario. But this approach of using try-lock is not free. It causes another problem called livelock. Because in try-lock situation, the thread may be trying the try-lock over and over and over again. So the both systems are running through the code sequence over and over and over again. So in that case, even though there is no deadlock situation, it is possible that progress is not being made. A way to resolve the livelock situation is at a random delay. So the livelock situation happens when the two threads, thread 1 and thread 2, and this one requires lock 1 and perform try-lock L2. At the same time, thread 2 locks L2 and perform try-lock L1. If the behavior of thread 1 and thread 2 is precisely synchronized and they perform the try-lock at the equal time interval, and then they keeps releasing and acquiring the lock L1 and L2 over and over again. So if the delay between the try-lock and go to lock, if the operating system or application can introduce a random delay between try-lock and acquiring the lock again, then it certainly decreases the possibility of livelock substantially. Another way of eliminating deadlock is using wait-free protocol. So we is powerful as hardware instruction. In that case, if we use a sophisticated data structure, then we can ensure the mutual exclusion without the lock. Let's look at the code. We have dealt with the data instruction called compare and swap. If the contents of a certain memory is equal to the value provided by the function, then assign a new value to the memory address, and all this step are executed in a single atomic fashion. That's compare and swap. So we can use compare and swap for the deadlock not to happen. Let's consider the following scenario. We can use a lock-free primitive to ensure the atomically increment the value by a certain amount. Consider the following function, atom increment. It has two parameters. First one is the address of the memory and then amount. Then what you'd like to do is increase the value of the memory by the specified amount. Using the lock-free data structure called compare and swap, it performs first. It retrieves the value of the memory address to the variable old and check whether the value and old are the same. The value of the value location and the old value of the old is the same. And if it is the same, then it gets out of the loop. If they're not the same, which means that right after retrieving the value of the address specified value pointer somewhere here, other thread might have updated the contents of the value pointed by this value location. Then the value of the first parameter and the value of the second parameter is not going to be the same. In that case, they fail, and then it returns 0, and then it'll try to retrieve the value again to the old. So it keeps iterating until it succeeds. So in this example, by using compare and swap, this function safely ensures the atomicity of the value increment function. So we do not need any lock, and it's a deadlock safe. However, there is a possibility of livelock. Let me provide another example of mutual exclusion that does not require any lock. This is a function insert. In insert, to ensure the atomicity of the operation, we surround this code with a lock acquire and lock release. There is lock acquire and lock release. And we can use wait-free. We can implement insert operation in wait-free manner as follows. The first part of the operations of inserting the object starts with allocating the object. The first one is like this. The first line, third line is the same. And then here we acquire the lock and insert the object and unlock. Here we perform a compare and swap operation. Let me use a figure to illustrate the example. This is insert with lock. First, we acquire the lock and we allocate the object, and then update the pointer of the object, point to the head of the list, and then update the head, point to the newly allocated list, and unlock the code. So this is basically 1 and 2 and 3. So these are 3 steps of inserting a node to the list. If we use compare and swap, we first allocate the node 1, and then we set the node 2, so that the next pointer of the newly allocated node points to the first node in the list. And then check whether the head and next is the same, which means that the head pointer and the next pointer points to the same item. If they do, then update the head, point to the newly allocated node. So using compare and swap, we can implement insert without any locks. Let me explain deadlock avoidance. In deadlock avoidance, we get the information about the locks the various threads might grab during the execution. And based on the information, we schedule the threads in a way to guarantee no deadlocks can occur. In some scenarios, a deadlock avoidance is preferable to the deadlock prevention. But the problem is that in deadlock avoidance, we need a global knowledge on the system. Let's consider the following scenario. There are 2 processors in 4 threads. And these are the lock acquisition demands of the threads. There are 4 threads: thread 1, thread 2, thread 3, and thread 4. And thread 1 lock requires 2 locks, lock 1 and lock 2. And thread 2 requires lock 1 and lock 2. And thread 3 requires lock 2 only. And thread 4 does not require any locks. And to avoid any deadlock, the smart scheduler can observe the lock acquisition scenario, and then make sure that T1 and T2 are not run at the same time. And then no deadlock could ever arise. The best way to do that is do not assign thread 1 and thread 2 to different CPU. And we can assign thread 1 and thread 2 to the same CPU like this. Using this approach, we can avoid deadlock. There can be more contention on the resources. For example, thread 1, in the same scenario, there are 4 threads: thread 1, thread 2, thread 3, and thread 4. And thread 1, 2, 3 acquires both lock 1 and lock 2. Then a possible schedule that guarantees that no deadlock could occur is to allocate thread 1, 2, 3 at the same CPU. But it may result in underutilization of the CPU, so the total time to complete the jobs is lengthened considerably. We can allow deadlock may occur. In that case, we have to take some actions. So if an OS froze, we have to reboot the system. Many database systems employ deadlock detection and recovery technique. The deadlock detector runs periodically, and the DBMS build a resource graph and check if there is any cycles. And in a deadlock, system needs to be restarted. So in this section, we covered 2 types of locks: non-deadlock bugs and deadlock bugs. And in non-deadlock bugs, we cover the atomicity violation and ordering violation. And to handle the deadlock, we can enforce the lock order, or you can employ lockless mechanism.